Okay, guys, we're going to go ahead and talk through a couple more of these practice problems. This gets a little bit easier because you see now we've got the specific heat table right in front of us. So let's start with number one. When 3.0 kilograms of water is cooled from 80 to 10 degrees Celsius, how much heat energy is lost? Especially for people who struggle with the math, let's just go ahead and write down our formula. We know that Q, which is the heat, equals mass times specific heat times delta T. And that delta T, remember, is final minus initial. So up here, when 3 kilograms of water, so there's our mass, we're going to go ahead and plug that value in, 3.0 kilograms. And it's cooled from 80 to 10. So in this situation, 10 is the final minus 80 initial. So our delta T here is a negative 70.0 degrees Celsius. And now it's wanting to know how much heat energy is lost. So we're looking for Q, which means we need to look up here to our table to find the specific heat of water. Now I put a hint down here for you because this table, I like it. There's actually 3 different specific heat values for water depending upon what state of matter it's in. And so when you read this question, you're thinking, well, how do I know if it's a liquid, solid, or a gas? Well, what you have to know is that if it's going from 80 to 10, it has to be liquid. Okay, because water freezes at 0 degrees Celsius. Well, if it's 10 degrees Celsius, it's definitely not frozen yet. And it boils at 100 degrees, which means it's not steam yet. So we're going to use this 4.2 times 10 to the third power as our specific heat. So we'll move our decimal 1, 2, 3. So that ends up being 4,200 for specific heat. And I'm out of room, so I'm going to leave my units off there. Notice that I left this value for mass in kilograms because the specific heat is given to me in kilograms. So I can leave that in kilograms, which is nice this go around. So when you put this in your calculator, we've got 3 times 4,200 times negative 70, and that negative is important, and we'll talk about why in just a second. So when you put it in your calculator, you end up with negative 882,000 joules. Okay, because we know that Q is a measurement of heat, which is measured in joules. Now pay attention to your significant figures. When you look at the original problem, how many sig figs do you have? I see that I have 2 sig figs here, 3 here, 3 here, and we always go with the smallest value, so I need to put this number into 2 significant figures. And so that would be negative 880,000 when I round joules. And just to get you in the habit of this, again, when you see that negative value, that is telling you that heat energy was lost. And if heat energy was lost, then that means that it is an exothermic reaction and that energy was exiting the reaction. Okay, so pretty straightforward on that one. Let's take a look at the next one. How much heat is needed to raise a 0.300 kilogram piece of aluminum from 30, there's the initial, to 150, which is the final. So again, let's go ahead and write down our formula. Mass times specific heat times delta T. And I'm looking for how much heat is needed, so I know I'm looking for Q. The mass in this situation is 0.300 kilograms times the specific heat of aluminum. So again, I've got to look up here to my table. I see that the specific heat of aluminum is 9.0 times 10 to the 2. Note what units that's in. We're going to move our decimal 2 places to the right, and so that would be 900.
Mama.
Yes, baby.
My coach time has ran out on his
Okay,
iPad,
can you
and
tell?
I'm so upset about
Can
it.
you tell him to bring me his Kindle Fire, please?
Yeah.
Tell him to bring it to me. Okay, and then right here to find the temperature, there's 150 is our final minus 30 initial, so that would be 120. So now 0.3 times 900 times 120 into your calculator is going to give you 32,400 joules. And let's go back and look at sig figs. Here we have 3 sig figs, 3 sig figs, 3 sig figs. And look at that. There's 3 sig figs in our answer. And so now endothermic or exothermic, it is definitely an endothermic reaction. Just a second, everybody. Okay, sorry about that. We're going to go ahead and take a look now at calculate the temperature change when. So again, let's just go ahead and write out our formula. Q equals mass times specific heat times delta T. And here we've got 10 kilograms of liquid water loses 232 kilojoules of heat. So several things going on in this problem, and let's just try to start with the first. we see loses 232 kilojoules. So that means that's definitely going to be a negative 232 joules because it's being lost. Now, we don't deal in kilojoules. We're going to get this to joules. And if you remember your prefixes, then this won't be an issue. Okay? We know that 1 kilojoule, because remember that prefix kilo means 1,000, represents 1,000 joules. And so now all we have to do is multiply 232 times 1,000, gives us a rather large number of negative 232,000 joules. So there's that Q that I need. I'm going to go ahead and plug that into my equation. Negative 232,000 joules equals, the mass here was 10.0 kilograms times liquid water would be 4.184, or the equation up here gives you 4.2 times 10 to the 3. So we're going to move that 1, 2, 3, 4,200. And then we're trying to see what the temperature change is, so we're actually looking for delta T here. My son is attacking me currently with a bulldozer, so I'm sorry if you hear that. From here, it's just all for a variable. So we're going to multiply the 10 times 4,200, and then we're going to do 232,000 divided by that answer. And we get 5, that delta T equals 5.52 degrees Celsius. 3 significant figures, and my answer also has 3 significant figures. Okay.
Mommy?
Yes, baby. Okay, sorry about that pause again. In this one, we have 1.96 kilojoules of heat are added. So added would be endothermic to 500 grams of copper. Again, several different conversions are going to take place here. The first one, we've got to get rid of that 1.96 kilojoules. So we're going to do the exact same thing and convert that into joules. And think back to dimensional analysis. We know that 1 kilojoule represents 1,000 joules. And so that's going to end up giving us 1,960 joules. We know the specific heat of copper. Let me just come over here and rewrite this. 1,960 joules. It tells me I've got 500 grams of copper. But remember, when we're looking up here at the specific heat of copper, sorry, let me shift down here. We're looking up here, that is given to us in kilograms. So we're allowed to use this value, but we've also got to change our mass to kilograms. So what was that? 390 is the specific heat. But again, we've got to change this 500 grams into kilograms. So that's going to end up being 0.500 kilograms times 390. That's the specific heat. And again, we are looking to see what the temperature change is, delta T. So same thing, we're going to take 1,960 divided by 0.5 times 390. And we are going to get, when we put it in our calculator, 10.05 degrees Celsius equals delta T. Let's look back originally. 3 sig figs here, 3 sig figs here. So guess what? We want 3 sig figs, which would be 10.1 degrees Celsius. That's what our delta T value is going to be. And note also that positive Q would mean that that's an endothermic reaction. One more on this page, guys. Number 4. We've got 2.52 times 10 to the 4th of heat are added. So that's going to be a positive value. So let's go ahead and we're going to write Q equals mass times specific heat times the final temperature minus the initial temperature. Why did you write it like that, Miss Vaughn? You're going to see in just a second. So here is my Q value. I'm going to go ahead and plug that in. 2.52 times 10 to the 4th joules equals, the mass here is 2 kilograms of mercury. I'm going to leave that as kilograms because, again, the specific heat values that are given to us up here in the table have kilograms. So I'm actually going to leave that as kilograms. I don't need to change that. So we've got 2.0 kilograms times the specific heat of mercury, according to the table, is 140. And that is in joules per kilogram degrees Celsius. times, here it tells me the final temperature is 130, and it's asking me for the initial temperature, which is why I wrote it like that. So my final temperature is 130 degrees Celsius minus what is that initial temperature is what I'm looking for. And this will become important actually on Monday when we do lab number 1 over specific heat. So from here, guys, it's solving for a variable. 2 times 140 is going to give me 280. So I'm just going to drop everything down here. And all I just did in that step was combine this value and this value, and I get 280. And then I'm going to bring over this 130 degrees Celsius minus initial temperature. Now remember what you have to do here. You could do two things actually. You could divide this over or you could distribute it. I'm going to go ahead and distribute the 280 to the 130, and that is going to give me 36,400 minus 280 times T is 280 T. And then again, I'm just going to bring down my original Q. I am running out of room, but the next thing that you would want to do here is subtract 36,400 from both sides. And when you do that, you get negative 11,200 equals negative 280 for that initial temperature. And again, how are we solving for that initial temperature? Now you're going to divide both sides by negative 280. And when you do that, you get 40. So let's kind of bring over here 40 degrees Celsius. Now let's look at sig figs. I've got 3 sig figs here, 2 here, 2 here. So if I would like for my answer to have 2 sig figs, not too hard, we're just going to add a decimal right there. And that is going to represent the initial temperature that we were looking for. Okay, and that one's a little bit more mathy, but everybody should be capable of doing that. That's just basic algebra, solving for a variable.